All right, welcome back. Sorry, my recorder kicked me out, so we're on part two, but we're in the same topic. So we are in number 9, course aggregate content. Okay, so we know the cement content. Okay, so knowing the number 9, course aggregate content, knowing the maximum size of course aggregate and the finest modulus. There's that finest modulus, a fine aggregate. So basically what that number is, it helps us determine the proper ratio between coarse aggregate and fine aggregate so we get a very well-graded mix. All our voids are filled to make a nice well-graded mix so we have a good strong concrete. Select the bulk volume ratio per cubic yard of concrete of the coarse aggregate in the mix from table 15.4. Knowing the dry rotted unit weight of the coarse aggregate. Okay, dry rotted unit weight. Okay, so what is that? That is the dry unit weight. So literally, what you do is you take a bucket, you weigh a bucket. Okay, you you put in dry aggregate, of course, aggregate in layers, and you gently tap it in there, and you keep filling it up until you get to the top of the bucket, because we know the volume of that bucket. Then I weigh it, and then we can calculate the density. So number of unit weight is density. Okay, it's a really a simple test. Okay. So knowing that, and then calculate the oven dry weight of the coarse aggregate in PCY, oven dry, there it is, oven dry weight of coarse aggregate equals dry rotted unit weight times 27 cubic feet per cubic yard times the bulk volume ratio. All right, nominal maximum aggregate size. Okay, so this is your coarse aggregate size, 3/8, half, okay, and then my finest modulus. All right, so if I have 2.50, obviously if I'm using 3/8 inch, 0.48, 0.50, I interpret it as 0.49. Okay, so you linear interpolate depending on what your finest modulus is. And that'll give us the amount of coarse aggregate that we're going to use per cubic yard. Okay, so admixture doses. Determine the total volume of admixtures per cubic yard of concrete to be added. In the case of air entrainment, the volume of air added is equal to maximum air content from step 5 multiplied by 27 cubic feet. Okay, so, all right, so we determined that if we're using air entrained concrete, and I think I can't remember which example I wanted to use because I have a severe exposure. I'm using 2-inch maximum size aggregate. I'm using 6% air. Okay, so that, remember, that's tiny air bubbles. That's physical volume space. Okay, so if I take 27 cubic feet times 0.06, that is actually how many cubic feet of airspace that 6% air will equal in that cubic yard of concrete. Okay, so that's what that is saying. And the example hopefully will clarify that. Okay, all right. Okay, so, and then, well, there's also admixtures, which there's examples. All right, fine aggregate content. Knowing the oven dry specific gravities. You just learned about this week. And weights of the water, cement, and coarse aggregate in the volume of air and admixtures. Calculate the total volume of ingredients, cement, water, coarse aggregate, admixtures, and air in the mix at this time. Okay. Remember, everything has to equal 27 cubic feet. Okay. So how do we do that? We know density, gamma, is weight divided by volume. We know the unit weight of water is 62.4 pounds per cubic foot. Remember this formula? Yeah, total weight equals weight of solids times 1 plus the water content. Now remember, if we have absorption rates, we can turn this into our absorption water content. Okay. Specific gravity oven dry, or G oven dry, is the unit weight oven dry of the water divided by the unit weight of water. And remembering, total percent, water percent total equals water content absorbed plus water content of free water. Okay, so we just went over this this week. Okay, so remember, how do I get my unit oven dry unit weight or dry unit weight? I take my unit weight of water times my specific gravity. Okay, all right. So figuring out my weights, and subtracting the total volume from 27 cubic feet, I know how many cubic feet of fine aggregate I need, and then I can back calculate a weight, okay? And the example will make sense. All right. 12, 1 cubic yard is SSD design. Knowing the absorption values for fine and coarse aggregates, calculate the SSD weights of the fine and coarse aggregates. Do not make any adjustments to the water content. The weights calculated to this point are design weights for 1 cubic yard of concrete SSD, saturated surface dry. Okay. 1 cubic yard actual water content design. Knowing the oven dry weights of the fine and coarse aggregates and the actual water contents for each calculate the actual weights of each aggregate. Also determine the weight of any free moisture or water or deficit of and adjust the water content accordingly. Okay, so this is the key. Remember me at telling you that you need to understand moisture conditions of aggregate. All right. Okay, so we have oven dry, we have saturated surface dry, and we have wet. All right, so if our aggregate is oven dry, natural water content of 4.6%, okay, and an absorption of 1.6%, okay, that means we have free water, right? Because 1.6% of the water is, so our water content is greater than our absorption water content. That means we have free water. Now, if we have an absorption of 1.6% and a natural water content of 1%, that means we are below our SSD, correct? That means some of that water will suck into the aggregate, right? So it's very important that you kind of visualize that. So we need to adjust. So basically in a design example, if we need 270 pounds of water, okay, and depending on our water content and our absorption, we may have to subtract mixed water from that, or we may have to add mixed water to make sure we have enough water to hydrate that. Okay? And then determine the actual batch weights based on the volume to actually be produced. Okay, so an example will explain this guy. All right, and adjust weights. Adjust the weights as necessary for slump, workability, and relative yield. And we'll go over relative yield. So that is going over this sheet. All right, so now let's take time and go through an example. So I'm going to read through this, and then I'm going to show you my calculations, and then I'll go through the first one, and then I'm going to let you read through the second two. I think there's 2 or 3 here. And then you can start doing your homework. I gave you the answers in homework, so you need to be able to understand this. Okay? All right. Concrete is required for a reinforced foundation wall for an unheated building. Unheated building. So if it's unheated, are we going to get freeze thaw? Yes. It's a foundation wall, right? It's below ground. In Green Bay, Wisconsin, the wall will be 8 inches thick between forms. The clear space between reinforcement bars is 4 inches. A minimum of 3 inch of concrete cover is required over the reinforcing bars. A specified compressive strength, F prime C, of 3,500 pounds per square inch is required at 28 days. In addition, based upon the geotechnical investigation, the soil was found to have moderate sulfate exposure. Okay, the following materials are available for use. Cement type 1 with a specific gravity, SPGR is the abbreviation for specific gravity of 3.15. 3/4 inch gravel with some crushed particles with an oven dry specific gravity of 2.68, absorption of 0.5%, a dry rotted unit weight of 100 pounds per cubic foot, and a moisture content of 2.0%. Fine aggregate, natural sand with an oven dry specific gravity of 2.64, absorption of 0.7%, finest modulus of 2.80, and moisture content of 6%. Air entrainment. Okay. Now, just because I list air entrainment here doesn't mean that you got to read the problem to make sure I'm actually going to use air entrainment. Are we in an unheated building, freeze thaw? So yes, this problem we're going to use air entrainment. Air mix equals 1/2 to 1 ounce per sack of cement. So each sack of cement is 90 pounds, right? to entrain 3% to 6% air. Okay. Develop a trial mix for 1 cubic yard of concrete based on saturated surface dry weights. Develop a trial mix for 2 cubic feet of concrete based on actual wet weights, the actual weights. Okay? All right. So I'm going to go flip back and forth between here and here. So let's go back to, okay, let's go back all the way up, and then we'll go through this design, and then it'd be enough information to get you started. And then, of course, I'm more than willing to answer questions. All right. So here we go. Step 1, specify compressive strength. So I told you in the problem that we need 3,500 PSI, specified design strength. Table 15.1. All right. Exposure category. W1, F1, S1, 4,000 PSI. So let's go back to that. Why did I choose that? Let's see. Concrete intended to have low permeability when exposed to water or moderate sulfates. So did I describe moderate sulfates in the problem, in the sample problem? Yes, I did. Right? Have moderate sulfate exposure. Right? So look here. I have, let's see, concrete exposed to freezing and thawing because it's unheated with limited exposure to moisture. Okay. Concrete intended to have low permeability, all right, when exposed to water, foundation wall, or moderate sulfates. Okay, what's my worst case scenario? If I look here, I have 4,000 and 3,500. So I have moderate sulfate. So I want to design it for 4,000. But my structural design is 3,500. So I am going to choose 4,000. Okay? Step 2, required average compressive strength. Table 1510, F prime C plus 1,200 PSI. Okay, let's go to table 2. 3,000 to 5,000. I'm at 4,000. F prime C plus 1,200. It'll give me F prime CR. Okay, so 4,000 plus 1,200. So I'm going to design this concrete of an average compressive strength of 5,200 pounds per square inch. All right, step 3, water cement ratio. Okay, so table 15.1. Let's go back to the table 15.1. All right. W1, S1, right? Moderate sulfates. Water cement ratio 0.50. Okay. Table 15.2. Let's go down to 15.2. S1, moderate sulfates, right? Maximum water cement ratio 0.50. Okay. Table 15.3, use F prime CR and air entrained, exposed to freeze thaw, linear interpolate. All right. I kind of showed you how you linear interpolate. Okay, so I kind of went through this process here to help you go through linear interpolation. Okay, so let's go look at this guy. So I'm at 5,200, right? Air entrained concrete, because I know I'm in a freeze thaw environment. So my water cement ratio is 0.32 to 0.40, somewhere in between there, right? So if I do my linear interpretation, I've got 0.38. Okay, so I'm going to pick the lowest one out of these 3. Lowest water cement ratio. So there's my water cement ratio, 0.38. Okay. All right. Step 4, maximum coarse aggregate size. Checks the maximum size coarse aggregate. Perform all checks. All right. So basically, 1/5 of the narrowest dimension between the sides of the forms. So I told you the distance between the forms, that's a foundation wall, is 8 inches. Right? So number between the sides of the forms. Form. Okay? So if I take 1/5 times 8 inches equals 1.6 inches. That's the maximum size coarse aggregate. Okay? Next check. 3/4 of the clear space between individual reinforcing bars or wire fabric. I told you we have 4 inches between our reinforcing bars. So 3/4 of that is 3 inches. So I'm allowed a maximum 3-inch aggregate, 3-inch nominal aggregate size. Okay? This one, 3/4 space between reinforcement and forms. Okay. So I told you I wanted a minimum space between the form and the nearest reinforcement is 3 inches. So my maximum 3/4 of 3 inches is 2.25 inches. Okay. All right. So so a third of the slab thickness, it's not a slab, so we don't have to, it's a non-applicable. All calculated spaces are greater than coarse aggregate, which is 3/4 inch diameter. Because of the problem is saying what are the materials that I got. Coarse aggregate, 3/4 of an inch, nominal aggregate size, right? So when I do my checks, I'm using 3/4 of an inch, and that is smaller than all of these. So if I wanted to choose, I could actually use 1.5 inch nominal aggregate size right here. See this? This is my smallest number of these, so I can actually use 1.5 inch nominal aggregate size. That will work in this reinforcement configuration. Step 5, maximum air content. It's exposed to freeze thaw. Okay, so we go to table 15.5. All right, so 3/4 inch, air entrained, moderate exposure, right? 5% plus or minus 1% is 6%. Okay, 5% is our exposure F1. So we're going to design for 6.0% air. Slump. Okay, did I specify a slump? I did not. Did not specify a slump. Okay, reinforced foundation walls and footings. Plain footings, caissons, and substructure walls. Beams and reinforced walls. Okay, buildings and columns, pavements and slabs, mass concrete. So I have a reinforced foundation wall, so my maximum slump is 3 inches, my minimum slump is 1 inch. You always want to design for the maximum slump. Always design for the maximum slump. Okay, so that's 3 inches. All right, so now I have my coarse aggregate size, I have my air, and I have my slump. Okay, now how much water do I need per cubic yard? Okay, table 15.5. I go back up. I have 3/4 inch aggregate. I'm air entrained. I have a 3 inch slump. I need 305 pounds of water per cubic yard of concrete. Okay. All right. However, do I need to subtract anything because of my aggregate type? What kind of aggregate type did I say I had? Coarse aggregate has some crushed particles. So that means I have to subtract 35 pounds. Okay. So now I am at 305 pounds per cubic yard. That's based on the table. And I'm subtracting 35 pounds per cubic yard. So now I'm going to use 270 pounds per cubic yard of concrete, of water. All right. Step 8, cement. Knowing the water cement ratio from step 3 and the amount of water from step 7, okay? So there's a little error right here. So this should, water cement ratio is 0.32. Actually, I apologize. See this little 2 right here? That should actually be an 8, or is it a 2 or is it an 8? It's an 8, right? This is our water cement ratio. This is the lowest one of these, okay? So I apologize for that. See if you're paying attention, right? So water cement ratio equals 0.38. So I'm from step 7, I know there's water, there's 270 pounds per cubic yard per pounds of cement equals 0.38. I solve for C, right? And then I get 711 pounds per cubic yard based on the math. So again, this number right here should be it should be an 8. An 8. Let's see, I may fix that later. All right. So Freeze thaw and sulfates. We have moderate sulfates. We are in a freeze thaw environment. We need a minimum of 564 pounds per cubic yard. Yes. Placement underwater. Well, we're not placing it underwater, but we can because we're at 711 pounds. Flat work. NA, it's not a flat work, right? It is table 15.6. Okay, it's a foundation wall. So that means we are okay using 711 pounds per cubic yard. We don't have to bump it up based on these criteria. Okay, so that was step 9. Step 8. Step 9, coarse aggregate. Using the finest modulus of the fine aggregate of 2.80 and 3/4 inch coarse aggregate, the bulk volume ratio equals 0.62. All right, let's go back to that. So in the problem, we did the cement content. All right, so we were using 3/4 inch coarse aggregate. We have a 2.80 finest modulus that was given in the problem statement. Our bulk volume ratio is 0.62, right there. Okay. All right. So with that, oven dry weight of coarse aggregate, I give you this of 100 pounds per cubic foot. There are 27 cubic feet per cubic yard times my bulk volume ratio. So that means I am going to use 1,674 pounds per cubic yard of coarse aggregate. That is based on dry, oven dry weight. Okay, so that was step 9. Step 10, admixtures. From step 5, we have 6% air content. Okay, so we want to use admixtures. Therefore, 0.06, I turn that into a decimal, times 27 cubic feet, because there's 27 cubic feet per cubic yard, I end up with 1.67 cubic feet of air volume. Okay, that little box that I have in my lab is 1 cubic foot. So that's how much air is actually in there, mixed in that concrete, in 1 cubic yard of concrete. All right, so now we got to figure out how to calculate admixture. So we want to add air entrainment, right? So if I go back up, so let me hit my page up. We know right here, we want to add this air mix 1/2 to 1 ounce per sack of cement to entrain 3% to 6% air. Okay? All right, so we can assume a 1/2 ounce will give us 3% air and 1 ounce will give us 6% air. So we're going to do a ratio. Okay, so remember, here's this finest modulus of a fine aggregate. Okay, it's from our previous. All right, so let's go back down. All right, so 1/2 to 1 ounce per sack yields 3% to 6%. We need to get to 6%. All right, so what I want to do is first I want to figure out how many ounces per 1% air. So 1/2 ounce will give me 3% air equals how many ounces per 1% air. I cross multiply. So I'm going to add 0.167 ounces per 1% air. Okay, it's not a lot if you think about it. Okay, so 0.167 ounces per sack per 1% times 6%. Okay, so equals 1.0 ounce per sack, which equals 94 pounds. Okay, so when I multiply 0.167 times 6, I get 1.0. Okay, all right. 1.0 ounces per 94 pounds, right? Okay, equals X pounds per 700 pounds per cubic yard. So that's how much concrete I have per cubic yard, or how much cement I have per cubic yard of concrete. Okay, all right. So with that, I solve for X. I cross multiply again. So that means I'm going to use 7.6 ounces per cubic yard of concrete. Okay, so I'm using 0.16 ounces per 1% per sack. So basically what this is doing is figuring out how many sacks I'm going to have and within 711 pounds per cubic yard, and then that's how I figure out. So I'm using 7.6 ounces per cubic yard for air entrainment. All right, step Step 11, fine aggregate. Okay, I made some errors here, but I corrected them. All right. So with that, so we have water, cement, coarse aggregate, fine aggregate, and air. Weight oven dry. W, weight oven dry, pounds per cubic yard. I know I'm using 270 pounds because that was all the way from where? So if we look, that was from right here, step 7. Remember, we pulled it from the table. We have to subtract. So we're using 270 pounds per cubic yard of water. We're using 711 pounds of cement per cubic yard, right? That was from step 8. And then from coarse aggregate, we're using 1,674 pounds per cubic yard. Fine aggregate, we don't know yet, okay? And air weighs nothing. All right, so unit weight oven dry, okay? We know water is 62.4 pounds per cubic foot, okay? Cement, so how do I do that? I take 62.4 pounds per the specific gravity of it times 62.4, and I will get the oven dry unit weight of the material. So 3.15 times 62.4, this is my unit weight. I don't know, so the coarse aggregate has a specific gravity, the fine aggregate has a specific gravity. Okay, so remember that's this relationship, right? That relationship that we went over this week. So this is specific gravity times unit weight of water. Specific gravity times unit weight of water. Okay, so now we know how much does it weigh per cubic foot. Okay, all right. Now, how do I calculate volume? Water. Okay, volume. Density equals weight divided by volume. Can I just solve for volume, right? Or rearrange this equation? Weight divided by density. Weight divided by density, I get 4.32 cubic feet per cubic yard of water. Same thing here. I get 3.62 cubic feet per cubic yard. Coarse aggregate, 10.01. And then from step 10, I calculate 1.67 cubic feet of air. If I add these up, I get 19.62 cubic feet, right? But we know there's 27 cubic feet per cubic yard, okay? So I keep saying okay. Sorry about that. So total volume of concrete has to equal 27 cubic feet. To calculate the volume of fine aggregate, add known volumes and subtract from 27 cubic feet. This will be your required volume of fine aggregate. Once you know the volume of fine aggregate, you can calculate the oven dry weight of fine aggregate using the density equation. Now I'm solving for density, right? Volume of fine aggregate equals, so 27 cubic feet minus the addition of all those, and I get 7.38 cubic feet. Now the oven dry weight of the fine aggregate is, rearranging this equation, 7.38 times the density, I get 1,215 pounds of fine aggregate. Okay, so now I just filled in this number. Okay, this is all an oven dry weight. Okay, step 12, 1 cubic yard SS design. Now, finally, we have some information here, right? Knowing absorption on the fine aggregate and coarse aggregate, you can calculate SSD weights using weight SS, this equation right here. Remember, instead of total, we can say SSD. All of these are dry unit weights, correct? Water doesn't change weight. Cement doesn't change weight. Coarse aggregate is dry. Fine aggregate is dry. Okay, so if my weight of solids equals 1,674 or 1,215 plus 1 plus my absorption content, I plug it into that equation. I gave you the absorption contents. This is my weights of my aggregates SSD. They went up a little bit, right? That's the weight of solids plus the weight of absorbed water. Okay? Now we add those up. There we go. That is the weight of our mix design of our ingredients SSD. So that answered letter A. Okay. Step 13 is calculate 1 cubic yard actual weights. Okay. I keep saying okay. I'm going to work on that. Knowing moisture contents, you can calculate actual weights. We use this formula again. Okay. We know our oven dry weights have not changed. Our SSD weights have not changed, right? We use our absorption water contents. Instead of using absorption water content, we're going to use the actual water content. So of here and here, and I give you that in the problem. Okay. Now, look what happened right here. 181 pounds per cubic foot. So why did I do that? Note, if the water content is greater than the absorption rate, there will be excess free water, which has to be subtracted from the mixed water. If the absorption rate is greater than the water content, water will have to be added to the mixed water. All right. So, coarse aggregate 1707. Okay. That is my actual weight that if I'm pulling my truck over a scale with the water in it is 1707 pounds. My SSD weight is 1682. So that means I have 25 pounds of excess water, of excess free water. Okay. Fine aggregate, 1288. Okay. Here's 1288. So that is the weight of aggregate per cubic yard of actual moisture conditions. 1288 minus my SSD weight. This is why we need to calculate SSD weights. Equals 64 pounds. So I have a total of 89 pounds of excess water. So my actual water will be 270 minus 89, which is 181 pounds. All right. That is why this changes to 180. So this is actual weights, because that is the actual water content of that stockpile sitting out in the yard. So I need to know what that water content is. So if I needed to subtract mixed water or add mixed water, this is why you need to understand moisture contents. All right. All right. So this is B. Okay. Or I'm sorry, that's not. So we need that before we can do this. Batch weights at actual water contents, 2 cubic feet. So that's a ratio, right? Two of those little boxes divided by 27. So here are my actual weights of my aggregate times that ratio. All right. So to batch 2 cubic feet of concrete, I'm going to use 13.1 pounds of water, 52.7 pounds of cement, 126.4 pounds of coarse aggregate, 95.4 pounds of fine aggregate, and 0.56 ounces of admixtures to get 6% air. So this is what answers B. We want to base it on actual weights. So this is why we always start from dry unit weights, because that moisture condition of the aggregate is going to change constantly. So if you understand, if I have my batch weights in the dry condition, and then I know my absorption, we can calculate what our actual weight should be when we're in a lab measuring stuff. All right. So that is that problem. Okay. So here's example problem 2. So what I want to do is go over C, because it's the same process. Okay. All right. Testing the trial batch indicated slump in strength to be within specification. However, relative yield was 1.10. Recalculate the 1 cubic yard SSD design to adjust relative yield to 1.0. So let me go to C, and then you'll be able to, it's the exact same process. Talk through it. All right. Yield equals total mass of materials divided by the density of concrete. Yield equals mass divided by density times 27. What this does is there's 27 cubic feet per cubic yard. So that's how we calculate yield. Relative yield is the actual yield divided by design yield. My design yield is always 1 cubic yard or 27 cubic feet. My actual yield is this guy right here. Okay. So literally what you do when you get your relative yield, if you're just going to take your weights, your SSD weights, and divide it by your relative yield. So if I am over yielding, which is 1.1, I'm making this number smaller. I'm making this number smaller, smaller, smaller. So I am reducing the amount of weights to get my yield to 1.0. I want to produce exactly 1 cubic yard of concrete. Now, if I'm under yielding, I do the same thing. If I'm under yielding, that's less than 1. So if I take 250 divided by 0.9, I'm actually going to add weights to my batch, and that'll give me 1. So remember me explaining that over yielding, under yielding. That's where this comes into play. Okay? So I just wanted to talk about that, but the process is the same. You go through the process. So you should now have enough information to go through your homework. Okay? I have those in Blackboard. I have the answers in Excel. You should be able to go through that homework and be able to work through these problems so you understand it. Okay? So thank you for your attention. Sorry for saying okay so many times. I'm learning, but we'll get there.